Swayam Prabha. Digital India. Educated India.
Now we come across the agent and environment and associated with next to talk about that reinforcement learning. So it's an overview of reinforcement is introduction to reinforcement learning and finite Bargo decision process, temporal difference learning like SA, RSA, Q learning, deep Q network, policy gradient methods, finite different policy gradient, reinforce, actor critic and synchronous reinforcement learning. These are all the overview, and let us go to the introduction to reinforcement learning. What is reinforcement learning? Learning from interaction with an environment to achieve some long term goal that is related to the state of the environment. So the goal is defined by reward signal which must be maximized. Agent must be able to partially or fully sense in the environment state and take action to influence the environment state. The state is typically described with a future vector. Next, exploration versus exploitation. So, we want the enforcement learning agent to earn lots of reward. The agent must prefer past action that have been found to be the effective at producing reward. The agent must exploit what it already knows to obtain reward. The agent must select untested action to discover reward producing action. The agent must explore action to make better action selection in the future, and trade off between the exploration and exploitation. Next, reinforcement learning system. Reinforcement learning system has a 4 main element. One is policy, next reward signal, value function, optional model of the environment. Policy. A policy is a mapping from perceived states of the environment to action to taken when those states. A reinforcement learning agent uses a policy to select action given the current environment state. Reward signal. Reward signal defines the goal. On each time the step, the environment sends a signal number called the reward to the reinforcement learning agent. So the agent is objective is to maximize the agent's objective is to maximize the total reward that it receives over the long run. So the reward signal is used to alter the policy. Next, the value of the function 1. The reward signal indicates what is good in the short run, while the value function indicates what is good in the long run. So the value of the state is the total amount of reward an agent can expect to accumulate over the future starting in that state. Compute the value using the states that are likely to follow the current state and the reward available in those states. Future rewards may be time discounted with a factor in the interval 0, 1. Value function 2 is use the values to make the evaluate the decisions. Action choices are made based on the value judgments. Prefer actions that bring about the states of highest value instead of highest reward. Rewards are given directly by the environment. Value must continually be re-estimated from the sequence of observation that an agent makes over its lifetime. So, model free versus model based. A model of the environment allows inference to be made about how the environment will behave. Example, given a state and an action to be taken while in that state, the model could predict the next state and the next reward. Models are used for planning, which means deciding on the course of action by considering possible future situations before they are experienced. Model based methods use models and planning. Think of this as a modeling dynamics P of S dash over S, A. Model free methods learned exclusive for trial and error. So, no modeling of the environment. This presentation focuses on model free methods. Next, on policy versus off policy. On policy, next on policy versus off policy. An on-policy agent learns only about the policy that it is executing. Off-policy agent learns about a policy or policies different from the one that is executing. Next, credit assignment problem. Given a sequence of states and action and the final sum of time discounted future rewards, how do we infer which action were effective at producing lots of reward and which action were not effective? How do we assign credit for the observed rewards given a sequence of action over time? So, every reinforcement learning algorithm must address this problem. Next, reward design. So, we need a reward design to guide the agent to achieve the goal. Option 1, hand designed reward function. This is a black art. Option 2, learn rewards from demonstrations. Instead of having a human expert tune a system to achieve the desired behavior, so the expert can demonstrate desired behavior and the robot can tune itself to match the demonstration. What is a deep enforcement learning? Deep enforcement learning is a standard enforcement learning where a deep neural network is used to appropriate either a policy or the value function. Deep neural network requires a lot of real or simulated interaction with the environment to learn, and lots of trials or interaction is possible in simulated environments. So, we can easily parallelize the trials or interaction in simulated environments. So, we cannot do this with the robotics, no simulation, because action execution takes time, accidents or failures are expensive, and there are safety concerns. Next, finite Markov decision processes. Markov decision processes mean MDP acronym. First you set states S, next set action A, and state transition probability P of S dash bar S comma A. This is the probability distribution over the state space given. So, we take action in the state S, discount factor nu in closed interval 0 comma 1, reward a function R such that S cross A to set of real numbers. For simplicity, assume the discrete rewards. For finite Markov decision process, if both S and A are finite. Next, time discounting. The understanding formulation nu equal to 0 across episodes in appropriate for episodic task in which the agent environment interaction breaks into episodes. So, it is a multiple trials to perform a task. Example, playing breakout, each run of the game is an episode. The discounted formulation 0 less than nu less than or equal to 1 is appropriate for counting tasks in which the interaction continues without limit. Example, vacuum cleaner robot. This presentation focuses on episodic tasks. Next, agent environment interaction. Agent and environment interact at each of the sequence of discrete time steps 0 to t, where t can be infinite. At each time step t, the agent receives some representation of the environment state st in S and uses this to select an action at in the set of A of st of available given that state. So, one step later, the agent receives a numerical reward R suffix t plus 1 and finds itself in the new state S suffix t plus 1. Next, environment interaction 2. At each time step, the agent implements the stochastic policy or mapping from the states to probabilities of selecting each possible action. So, the policy denoted by pi t, where pi t of A bar S is the probability of taking action A when in state S. A policy is a stochastic rule by which the agent selects action as a function of states. The reinforcement learning methods specify how the agent changes its policy using its experience. So, action selection at time t, the agent tries to select an action to maximize the sum gt of discounted rewards received in the future. So, MDP dynamics, given current state S, action A in the state, the probability of the next state S and the next reward R is given by the state value function 1. The value function are defined with respect to the particular policies because future rewards depend on the agent's action. Value function is give the expected return of the particular policy. The value V over pi of S of the state S under the policy pi is expected return when starting in state S and following the policy pi from the state onwards. So, the state value function V pi of S for the policy pi is given below. Note that the value of the terminal state of is always 0. Action value function. So, the value Q over pi of S comma A is taking action A in state S under policy pi is defined as a expected return starting from S, taking the action A and thereafter following policy pi. So, Q suffix pi is the action value function for policy pi. Next, Bellman equation. The equation expresses the relationship between the value of the state S and the values of its successor states. So, the value of the next state must equal to the discounted value of the expected next state plus the reward expected along the way. Bellman equation 2, the value of the state S is the expected value of the sum of the time discounted rewards starting at current state given current state S. So, this is expected value of R plus the sum of the time discounted rewards overall successor state S and all next rewards R and overall possible action in the current state S. Next, optimality. The policy is defined to be better than or equal to the another policy if its expected return is greater than or equal to that of the other policy for all states. There is always at least one optimal pi that is better than or equal to all other policies. All optimal policies has the same optimal state value function V star which gives the maximum expected return for any state S over all possible policies. All optimal policies share the same optimal action value function Q star which gives the maximum expected return for any state action pair over all possible policies. Next, temporal difference learning. What is TD learning? Temporal difference learning is a TD learning. The prediction problem is that of estimating the value function for a policy pi. The control problem is a problem of finding an optimal policy pi star. Given some experience following a policy pi, update estimate of V pi for non-terminal states occurring in that experience. Given current step T, TD methods wait until the next time step to update V of S of t, learn from partial returns. Next, value based reinforcement learning. We want to estimate the optimal value V star of S or action value function Q star of S comma A using a function approximator. So, V of S comma theta or Q of S comma A comma theta with the parameters theta. So, this function approximator can be any parametric supervised machine learning model. So, recall that optimal value is a maximum value achievable under any policy. Next, update rule for TD 0. At time t plus 1, TD methods immediately form a target of R suffix t plus 1 plus nu of V of S suffix t plus 1 and make a useful update with step size alpha using the observed reward R suffix t plus 1 and estimate V of S plus S suffix t plus 1. So, update is a stop size times and the difference between the target output and the actual output. Update rule intuition. The target output is a more accurate estimate of V of St given the reward R suffix t plus 1 is known. The actual output is our current estimate of V of St. So, we simply take one step with our current value function estimate to get more accurate estimate of V of St and then perform an update to move V of St closer towards a more accurate estimate. Now, we have a TD algorithm, 0 algorithm, input the policy pi to be evaluated, initial V of S arbitrarily, V of S equal to 0, repeat for each episode, initial S, repeat for each step episode and A action given by pi for S, take action A, observe R comma S dash. So, V of S is V of S plus alpha of R plus nu of V of S dash minus V of S and S equal to S dash until S is terminal. This is a pseudocode of a tabular TD. And SRSA on policy TD control is state action, reward state action, learn an action value function instead of state value function. Q pi is the action value function for the policy pi. Q values are the values of Q suffix pi of S comma A for S in S, A in A. So, state action, reward, state action experience are used to update Q values. Use TD methods for prediction problem. SA or SA update rule, we want to estimate Q over pi of S comma A for the current policy pi for all state S and action A. The update rule is similar to the TD0, but we transition from state action pair to state action pair and learn the values of the state action pairs. So, the update is performed after every transition from a non-terminal state ST. If S suffix t plus 1 is a terminal, then Q of S suffix t plus 1 comma A suffix t plus 1 is 0. So, the update rule uses ST, AT, RT plus 1, ST plus 1, AT plus 1. Next, SA or SA algorithm and on policy TD control algorithm is initially Q of S comma A for all S in S, A in A of S arbitrarily and Q terminal state equal to 0. Repeat for each episode, initialize S, choose A from S using policy derived from Q and epsilon greedy, repeat for each step of the episode, take action A, observe R S dash, choose A dash from S dash using policy derived from Q and Q of S comma A is Q of S comma A plus alpha of R plus nu of Q of S dash comma A dash minus Q of S comma A where S dash to S, A dash to A until S is terminal. Q learning of policy TD control is similar to SA or SA but of policy updates. The learning action value function Q directly approximate the optimal action value function Q star independent of policy being followed. In update rule, choose action A that maximizes Q from S suffix t plus 1 and using resulting Q value plus the observed reward as the target. This method is off policy because we do not have a fixed policy that maps from states to action. So, this is why A suffix t plus 1 is not used in the update rule. So, the pseudocode is an off policy TD control algorithm initialize Q of S comma A for all S in S, A in A of S arbitrarily and Q terminal state is 0, repeat for each episode and initialize S, repeat for each step of episode, choose A from S using a policy derived from Q and epsilon greedy, take action A, observes R and S dash, Q of S comma A is Q of S comma A plus alpha into R plus nu of maximum of Q of S dash A of A minus Q of S comma A and S dash to S, then until S is terminal. So, this is a pseudocode of off policy TD control. Next, epsilon greedy policy. At each time step, the agent selection action. The agent follows the greedy strategy with the probability 1 epsilon. The agent selects a random action with the probability epsilon. The Q learning, the greedy strategy is the action A that maximizes Q given S suffix t plus 1. And for deep Q network is DQN. Introduce deep enforcement learning. It is common to use a function approximator Q of S comma A comma theta to approximate action value function in Q learning. So, deep Q network is a Q learning with a deep neural network function, approximate called the Q network and discrete and finite set of action A. Example, breakout as a 3 action, move left, move right, no movement and uses epsilon greedy policy to select actions. And Q networks, core idea is we want to neural network to learn a nonlinear hierarchy of futures or future representation that gives accurate Q value estimates. The neural network has a separate output unit for each possible action which gives the Q value estimate for that action given the input state. So, the neural network is trained using mini batch stochastic gradient updates and experience replay. Next, experience replay. The state is a sequence of action and observation start from st equal to x1, a1, x2, a2 and so on, xt minus 1, xt. Store agents experience at each time step et equal to st, at, rt, st plus 1 in a data set d equal to e1 to en, pulled over many episodes into replay memory. In practice, only store that last n experience tuples in the replay memory and a sample uniform from D when performing updates. State representation. It is difficult to give the neural network a sequence of arbitrary length as input. Use fixed length representation of sequence or history produced by the function phi of st. Example, the last 4 image frames the sequence of breakout gameplay. Next, Q network training. Sample random mini batch of the experience tuples uniformly at random from D. Similarly, Q-learning update rule, but use mini batch stochastic gradient updates. The gradient of the last function for a given iteration with respect to the parameter theta I is the difference between the target value and actual value is multiplied by the gradient of the Q function approximator Q of s comma a comma theta with respect to the specific parameter. Use the gradient of the loss function to update the Q function approximator. Next, loss function gradient derivation. We refer the neural network function approximator with the weight theta as a Q network. A Q network can be trained by minimizing sequence of loss functions Li of theta I that changes at each iteration I. So, Li of theta I equal to E suffix s, where A is approximately P of dot yi minus Q of s comma a comma theta I square, where yi is E s dash is approximately epsilon into r plus nu max a, Q of s dash a dash theta suffix I minus 1 bar s comma a is a target for iteration I, and rho of s comma a is a probability distribution over sequences s, and action a we refer to as the behavior distribution. The parameter from the previous iteration theta suffix I minus 1 and held fixed when optimizing the loss function Li of theta I. Note that the targets depend on the network weights. So, this is in contrast with the targets used for supervised learning, which are fixed before learning begins, and differentiating the loss function with respect to the weight, we arrive the following gradient. So, delta theta I of Li of theta I equal to E suffix s of a approximately P of I, s dash is approximately epsilon of r plus nu of maximum of Q of s dash a dash theta minus theta suffix I minus 1 minus Q of s comma a comma theta I of delta I of Q of s of a comma theta I. Rather than computing the full expectation the above gradient, it is often computationally expedient to optimize the loss function by a stochastic gradient descent. If the weights are updated after every time step and the expectation are replaced by a single sample from the behavior distribution rho and the emulator epsilon is respectively, then we arrive at the familiar Q learning algorithm. So, DQN algorithm is a deep Q learning with the experience replay, and pseudocode is initially replay memory D to capacity N, initial action value function Q with random weights. For episode 1, M do initialize sequence S1 equal to X1 and pre-processed sequence Phi1 equal to Phi of S1 for t equal to 1 to capital T do with the probability epsilon select a random action AI, otherwise select AI equal to maximum of Q star of Phi of St comma a comma theta, execute action AT in the emulator and observe reward RT and image X suffix T plus 1, set S suffix T plus 1 to ST, AT XT plus 1 and pre-processes Phi of T plus 1 equal to Phi of S T plus 1, store transition Phi T, AT, RT and Phi suffix T plus 1 in D. So, the sample random mini batch of transmission is Phi j, AJ, RJ, Phi suffix j plus 1 from D. For terminal Phi suffix j plus 1, corresponding set of y is rj. For non-terminal phi j plus 1, corresponding set of yi equal to rj plus nu of maximum of q of phi of j plus 1 comma a dash comma theta. So, perform the gradient descent step on yj minus q of phi j minus aj of theta the square according to the equation n for the loop. So, the comments, it was previously thought that the combination of simple online reinforcement learning algorithm with a deep neural network was fundamentally unstable. The sequence of observed data states encountered by online reinforcement, learning agent is non-stationary and online updates are strongly correlated. The techniques of DQN is stable because it stores the agent's data in experience, replay memory so that it can be randomly sampled from different time steps. Aggregating over memory reduces non-stationary and decorrelates updates but limits methods to off-policy reinforcement learning algorithm. Experience replay updates use more memory and computation per real interaction than online updates and require off-policy learning algorithm that can update from data generated by an older policy. Next, policy gradient method. What are policy gradient method? Before, learn the values of the action and then select action based on their estimated action values. The policy was generated directly from the value function. We want to learn a parameterized policy that can select action without consulting a value function. So, the parameter of the policy are called the policy weights. So, the value function may be used to learn the policy weights, but this is not required for action selection. Policy gradients method or a method for learning the policy weights using the gradient of some performance measure with respect to the policy weights. So, policy gradient methods seek to maximize the performance and so the policy weights are updated using gradient ascent. Then policy based reinforcement learning is search directly for the optimal policy pi star, can use any parametric supervised machine learning model to learn policies pi of a over s of theta where theta represents the learned parameters. So, recall the optimal policy is a policy that achieve maximum future return. So, here the notation is policy weight is theta, the policy pi of a over s theta which represents the probability that action is taken in state s with the policy weight vector theta. If using the learned values function, the value function weight vector is w and then performance measure is a eta of theta and then the episodic case eta of theta is v pi over s naught. Performance is defined the values of the start state under the parameterized policy. So, the policy approximation can be parameterized in any way to provide pi of a over s theta is differentiable with respect to its weights. To ensure exploration, we generally require that the policy never becomes deterministic and so pi of a over s comma theta is in the interval 0 comma 1 open interval. Assume it is a discrete and a finite set of action. Form a parameterized numerical performance h of s of a comma theta for each state action and can use the deep neural network as a policy approximator and use softmax so that the most preferred action in each states are given by the highest priority of pi of a over s of theta equal to exponential of h of s of a comma theta by summation of exponential of h of s comma b comma theta. So, these are all the types of a policy gradient. One is a finite difference policy, Monte Carlo policy and actor critic policy gradient. So, finite difference policy gradient compute the partial derivatives and performs the measure eta of theta with respect to theta k using the finite difference gradient approximation, compute performance measure eta of theta, perturb theta by small positive amount epsilon in the kth dimension and compute performance of eta of theta of uk plus epsilon where uk is a unit vector and 1 is in the kth component 0 elsewhere. So, the partial derivative is approximated by eta of theta plus uk epsilon minus eta of theta by epsilon. Here theta k is less than minus theta k plus alpha into n of theta plus uk epsilon minus eta of theta by epsilon and perform the gradient ascent using the partial derivative. It is a simple, noisy and inefficient procedure that is sometimes effective. The procedure work for the arbitrary policies can be non-differentiable. Next, reinforcement, the Monte Carlo policy gradient. We want the quantity that we can sample on each time step whose expectation is equal to gradient. We can then perform the stochastic gradient ascent with this quantity like theta suffix t plus 1 equal to theta t plus alpha into nu per t into gt of delta theta pi of at by st comma theta by pi of at by st theta. And reinforcement properties are on policy method, use the complete return from time which include all future rewards until the end of the episode. Reinforcement is thus a Monte Carlo algorithm and is only well defined for the episodic case with all updates made the retrospect after the episode is completed. Note that the gradient of log s is a gradient of x divided by x by the chain rule. So, the algorithm is Monte Carlo policy gradient method is episodic. So, start with input the differential policy parameter pi of a over s of theta for all a in s, s in s, theta in r power n, initial the policy weight theta, repeat forever, generate an episode s naught, a naught, r1 and so on, st minus 1, a suffix t minus 1 or t following pi of dot bar dot comma theta for each step of the episode t equal to 0 to t minus 1 and gt return from the step t and theta such that theta is alpha into nu power t of gt of delta theta log of pi of at by st of comma theta. So, actor critic method is method that learn approximation to both policy and value function are called actor critic methods. Actor refers to the learned policy, critic refers to the learned value function which is usually state value function. The critic is bootstrapped, the state values are updated using the estimated state values of subsequent states. So, the number of steps in the actor critic method controls the degree of bootstrapping. So, one step actor critic update rule is on policy method, the state value function update the rule to the TD of 0 update the rule. The policy function update the rule is shown below for n step actor critic simply replace g of suffix t with g of suffix t of n where theta suffix t plus 1 is theta t plus alpha into g1 minus b of st comma w into delta theta of pi of at by st comma theta by pi of at by st theta and theta t plus alpha into rt plus 1 into plus nu of v into st plus 1 w minus v of st plus w is delta theta pi of at by st comma theta by at plus st comma theta. And one step actor critic algorithm says that you put the input the differential policy parameter pi of a over s comma theta for all a in a, s in s, theta in r power n and differentiable state value parameterize v of s comma w for all s in s, w in r power n. So, the parameterized step size alpha is positive and beta is positive. So, the weight theta and the state value w repeat forever and initial s, I you take 1 while s is not terminal and a take pi of dot bar s theta, take action a, observe s dash r, delta equal to r plus nu v cap of s dash comma w minus v cap of s comma w and w is w plus b delta of delta w v s comma w, theta is theta plus alpha I delta of theta delta into log of pi a by s theta and I is r nu or nu I, s is s dash and s dash terminal then v bar of s dash comma w equal to 0. Next synchronous reinforcement learning. What is synchronous reinforcement learning? Use asynchronous next what is asynchronous enforcement learning? Use asynchronous gradient descent to optimize controllers. This is useful for deep enforcement learning where the controllers are deep neural networks which take a long time to train. Asynchronous gradient descent speeds up to the learning process. Can use one multi-core CPU to train deep neural networks occurrences instead of multiple GPUs. And next, parallelism. Asynchronously execute a multiple agent is a parallel on multiple instances of the environment. This parallelism decorrelates the agent data into more stationary process, since at any given time step the agent will be experience a variety of different states. So, this approach enables a larger spectrum of a fundamental on policy and off policy reinforcement learning algorithm to be applied robustly and effectively using deep neural networks. Use asynchronous actor learning, that is the agent. Think of each actor learner as a thread. Run everything on a straight multi-core CPU to avoid a communication cost sending the gradient and the parameters. Next, parallelism 2. Multiple actor learning running is a parallel or likely to be exploring different parts of the environment. We can explicitly use the different exploration policies in each actor learner to maximize this diversity. By running different exploration policies in different threads, the overall changes made to be the parameters by multiple actor learners applying update in parallel are less likely to be correlated in time than a single agent apply in online updates. No experience replay. So, no need for replay memory, we instead rely on parallel actors employing different exploration policies to perform a stabilizing role undertaken by experience replay in the DQN training algorithm. Since we no longer rely on experience replay for stabilizing learning, we are able to use on policy reinforcement learning methods to train neural network in a stable way. Next, asynchronous algorithm or one step Q learning. It is one step SRSA, is a n step Q learning and asynchronous advantage actor critic A3C. So, asynchronous one step Q learning is consists of each thread interacts with its own copy of the environment and at each step computes the gradient of the Q learning loss and use globally shared and slowly changing target network with the parameters theta when computing the Q learning loss. So, DQN uses a globally shared and slowly changing target network 2. So, the network is updated using the network is updated using a mini batch of the experience tuples drawn from replay memory. The gradients are accumulated over multiple time steps before being applied, which reduces the chance of multiple actor learners overwriting each other's updates. So, the exploration is giving each thread a different exploration policy helps improve robustness and generally improves the performance through better exploration, and use epsilon greedy exploration with epsilon periodically sampled from some distribution by each thread. So, the pseudocode of the algorithm is asynchronous one step Q learning pseudocode for each actor learner thread. Start from the initial thread step counter I t equal to 0 and initial target theta is theta, and then initial network gradient d theta is 0, get initial state S and repeat. Take action A and epsilon greedy policy based on Q of S comma A comma theta, receive new state S dash and reward R, and Y equal to R for terminal S dash, and Y equal to R plus nu of maximum of Q of S dash A dash theta minus for non-terminal S dash, and accumulate the gradient with respect to theta, then d theta equal to d theta plus dou by dou theta of y minus q minus s a comma theta the whole square, and choose s equal to s dash and t equal to t plus 1, t equal to t plus 1. If t mod I target is 0, then update the target network theta to theta. End if t mod I asynchronous update is 0 or s is terminal, then perform asynchronous update of theta using d theta and clear gradients d theta is to 0, end if until t is greater than t max. So, asynchronous one step SRSA is the same algorithm as asynchronous one step Q learning, except the target value used for Q of S comma A is different. So, one step SRSA uses R plus nu of q of s dash comma a dash comma theta as the target value. So, n step q learning is, we have been using one step q learning. One step q learning update the action value q of s comma a towards r plus nu maximum of q of s dash a dash theta, which is the one step return. Obtaining the reward r only directly affect the value of the state action pair that led to the reward. The values of the other state action pairs are affected only indirectly through the update value q of s comma a. So, this can be the learning process slow, since many updates are required to propagate a reward to the relevant preceding states and action, and use n step returns to propagate the rewards faster. So, n step return, n step q learning is updated towards the n step return, that is RT plus nu of R suffix t plus 1 and so on, nu power n minus 1 R suffix t plus n minus 1 plus maximum of R power n of q of s comma t comma n a. So, the result in a single reward directly affect the value of n preceding state action pairs. So, this makes the process of propagating rewards to relevant state action pairs potentially much more efficient. So, one step update for the last state, two step update for the second last state, and so on until n step update for the nth last state. So, accumulated updates are applied in a single step. So, the algorithm is: assume global shared parameter vector theta, assume global shared target parameter value theta minus, assume global shared counter t equal to 0, initially thread step counter t is 1, initially target network parameter theta minus is theta, initially thread specific parameter theta dash equal to theta, initially network gradient d theta is 0, and repeat, and clear gradients d theta is approached to 0, synchronize the thread specific parameter theta dash equal to theta and t start t, get state st, and repeat, take action at according to epsilon greedy policy based on q of st comma a comma theta dash, receive reward r suffix t and new state s suffix t plus 1. If t is t plus 1, capital T is t plus 1 until terminal st or t minus t start equal to t max. Therefore, r can be expressed the function for t terminal st is 0, for non-terminal maximum of q of st comma a of theta minus. For I belongs to t minus 1 to t start, and do r ri plus nu r, accumulate gradients with respect to theta dash. Therefore, d theta equal to d theta plus dou by dou theta dash of r minus q of si comma a comma theta dash square. Now, n for perform asynchronous update of theta using d theta. If t mod I target is equal to 0, then theta dash to theta end if until t is greater than t max. A3C maintains a policy of pi of at over st of theta and estimate the value function v of st comma theta v, and we have to go n step actor critic method. The value based method use parallel actor learners and accumulate updates to improve the training stability. In practice, the policy approximation and the value functions have some parameters, and use a neural network that has one softmax output for the policy of pi of at over st comma theta and one linear output for the value of the function v of st comma theta v with all non output parameters shared. The advantage definition is: for one step actor critic method with a learned policy, a learned value function, the advantage is defined as a of at comma st equal to q of at comma st minus v of st. So, the quantity RT minus v of st comma theta v is an estimate of the advantage. The estimate is used to scale the policy gradient in an actor critic method. So, the advantage estimate for an n step actor critic method is shown below: summation I equal to 0 to k minus 1 nu power I of r suffix t plus I plus r power k of v of st plus k comma theta v minus v of st comma theta v, and based on this algorithm. So, the pseudocode for each actor learner thread is global shared parameter vectors theta and theta v, and take the counter t equal to 0, thread this specific parameter theta dash and theta v dash, and initially step counter is t equal to 1 and repeat, reset the gradient d theta is 0 and dv is 0 and synchronize the thread specific parameter theta dash is theta and theta v dash is theta v, then start t, get state st, repeat, perform at according to the policy, receive reward r suffix t and new state s suffix t plus 1 and t is t plus 1, capital T is t plus 1 until the terminal state st or t minus t start equal to t max. Therefore, we have a function r for terminal st 0, for non-terminal st we have v of st comma theta v dash, where I varies from t minus 1 to t start, do r equal to r a plus nu r, accumulate the gradient with respect to theta dash, d theta maps to d theta plus theta d dash of log pi of ai by si comma theta dash into r minus v of si comma theta v dash, accumulate gradient with respect to theta v dash and d theta v maps to d theta v plus dou by dou theta v dash of r minus v of si comma theta v dash whole square, and n for perform the asynchronous update of theta using d theta and of theta v using d theta v until t is greater than t max. So, the summary is get faster training because of parallelism, can use the policy reinforcement learning method, diversities exploration can lead to better performance than the synchronous method. In practice, on policy A3C algorithm appears to be the best performance asynchronous information. A3 algorithm appears to be the best performance asynchronous reinforcement learning method in terms of the performance and the training speed. So, one may refer the reinforcement learning by Karan Karpalia, can get further information. Thank you.